All right, welcome to The Explainer. Today we're going to tackle a topic that makes a lot of programmers nervous: dynamic programming. But what if I told you the secret to crushing it isn't about being some kind of genius? What if it's just about learning a simple, repeatable method? Let's break it down. So many of us, myself included, have hit this wall. You look at a DP solution and it feels like it was just pulled out of a hat, right? Like some kind of magic trick. But here's the thing. It's not. There's a logical framework, a step-by-step process that turns all that magic into a method you can actually use every single time. So where do most of us start? Well, usually with brute force recursion, where we just tell the computer to try all the possible ways. And hey, it's a totally intuitive first step, but it's like using a bicycle in a rocket race. It's just way too slow, and it almost always leads to that dreaded time limit exceeded error you see in coding challenges. We need the rocket. So in this explainer, we're going to follow this exact 6-step journey. We'll break down the initial problem, learn the absolute core rules, and then build our way up to a fully optimized solution that you can apply to tons of different problems. Okay, let's start with where things usually go wrong. First up, let's really get to the heart of why our gut instinct, that simple brute force recursion, just doesn't cut it most of the time. So when you tell a function to explore every single path, it acts like a really inefficient explorer. It keeps visiting the same places over and over and redrawing the same parts of the map again and again. In programming, we call this overlapping subproblems, and it's the #1 reason our code times out. We're just wasting so much time doing the same work. But here's the big secret. This is the part that changes everything. The key to mastering dynamic programming, well, it isn't really about DP at all. It's about getting really, really good at recursion first. If you can nail that, the rest is easy. And this quote from our source material just hits the nail on the head. Once you can actually frame any problem recursively, the rest of the steps, the optimization steps that turn it into a lightning-fast DP solution, they become almost mechanical. So the real work, the heavy lifting, is all in that initial setup. So how do you master that setup? You just follow these 3 golden rules. First, you have to define the state of your problem. Usually that just means using an index, or maybe 2 indexes if you're on a grid. Second, from that state, you just explore all the choices you can make. Can I jump 1 step or 2? Do I pick this item or not? And third, based on what the problem asks for, you take the best outcome from those choices. The minimum cost, the maximum profit, whatever it is. Okay, so you've written your recursive solution. It's probably way too slow, but it's correct. Now it's time for the first magic trick that gives you an easy win. It's a technique called memoization. You can literally think of memoization like giving your function a cheat sheet. Instead of trying to solve the same tough problem from scratch every time it sees it, the function just jots down the answer. The next time it sees that exact same problem, it doesn't have to think. It just looks up the answer it already wrote down in its notes. And the best part is that this process is incredibly mechanical. First, you set up a simple cache, usually just an array, to act as your function's memory. Then you add 1 simple check right at the top of your function. Hey, have I solved this exact problem before? If you find an answer in your cache, you just return it immediately. If not, you do the calculation like you normally would, but, and this is the key, right before you return the answer, you store it in your cache for next time. That's the whole trip. So this memoization approach, which we also call top-down DP, is a massive, massive performance boost. It's a game changer. But our optimization journey doesn't have to end there. We can actually take this same logic and flip it on its head for even more improvements. This right here, this is the whole playbook. You can solve almost any DP problem by following these 4 steps. You start with that slow but correct recursive idea. You add memory to it with memoization. Then you can transform that into an iterative solution using loops. We call that tabulation. And for the final polish, you can often shrink the memory it uses way down. So what exactly is this tabulation or bottom-up approach? Well, if memoization is like a CEO delegating tasks from the top down, tabulation is like an intern starting on the ground floor and building their way up. It solves the absolute smallest, easiest subproblems first, and then uses those results to build, step by step, towards the final answer, usually with some simple for loops. And this is where things get really clever. When you're using tabulation and filling out that table of answers, you have to ask yourself a critical question. To figure out the next answer, do I really need all the old answers, or do I just need the one I just calculated? If you only need the most recent results, you don't have to store the whole table. You can get by with just a couple of variables, which saves a ton of memory. Okay, so here's where it all really comes together. The true power of this isn't just solving one problem. It's realizing that this one single framework, this way of thinking, can be applied to whole categories of problems that look completely different on the surface. Let's see how this works. For DP on grids, what's your state? It's just your location, cell IJ. What are your choices? Move down or move right? Simple. For DP on subsequences, think of the famous knapsack problem. Your choice for every single item is always the same. Do I pick it or not pick it? And for something like partition DP, you're just trying every possible place you could split something, like a rod, and then finding the best split. See? The scenarios are different, but the core recursive question, what are my choices from this state, is exactly the same. So let's bring it all home. The most crucial point is that getting great at dynamic programming is not about memorizing hundreds of different solutions. That's the wrong way to go. It's about getting one powerful, repeatable method so deep into your brain that it becomes second nature. In the end, it really does just come down to this. You just have to ask two simple questions about your problem. First, what are the things that are changing each time I make a move? That's your state. And second, from here, what are all the possible moves I can make? That's your exploration. Once you can answer those two questions, you've pretty much cracked the core of the problem. So when you really look at it this way, when you focus from the recursive foundation first, and then just follow the simple mechanical steps of optimization, memoization, tabulation, and space saving, it's not magic anymore, is it? It's just a pattern. It's a method. And it's a method that can become your new programming superpower.